So you can tell that extreme space weather is a young field in terms of disaster response because this is the best diagram we have to explain the hazard of space weather. It's not exactly snappy, but this is the summary, right? The sun causes flares and coronal mass ejections. The radiation and the CMEs come in and they hit spacecraft, which can damage the spacecraft with electrostatic charging or radio interference, solar cell damage, or it can cause computer upsets. If you're an astronaut, you really don't want to be in space when there's very intense radiation. More down-to-earth considerations, if you're in a very high altitude passenger plane, your radiation dose is elevated. The atmosphere isn't as thick above you, so more radiation gets through. This isn't a direct risk to life, right? You don't have to worry about getting on a plane when there's a solar storm. However, if you're aircrew, a pilot or so on, your radiation by law is now monitored. So aircrew and pilots are radiation workers, their dose is tracked, and they can't exceed a certain dose in a year. Then we have GPS signals coming to the ground, so we might get navigation errors. We have ground-induced currents in train lines, pipelines, and the electrical transmission system. And our radio might be disrupted. So this is the kind of big summary of impacts. Let's look at some of these in a bit more detail. So electromagnetic radiation. So when a flare happens and you get X-rays come and hit the top of the atmosphere, the ionosphere thickens. So this is a diagram or a cartoon showing different layers of the ionosphere. When the radiation from the sun is very intense, we get extra layers and we get thicker layers, and that attenuates the radio signal. So that might not be a huge problem. You think, no one uses radio anymore, right? That's just what I listen to in the car and that's it. But actually, there's a number of important impacts here. Aircraft are not allowed to take off unless they can prove they've got adequate radio connection between takeoff and landing. There's plenty of things that still operate on radio. The UK, it's closing down, but the UK still has a national clock that runs by radio. Also, we communicate with all our telecommunications satellites by radio. So although radio for personal use has kind of decreased a fair amount, and you may not care about this for that reason, quite a lot of our advanced technology still depends on some kind of radio signal. When you have a very extreme flare, you can get radio blackout. So the sunlit side of the Earth, the ionosphere can get so thick that radio communications, particularly at high frequencies, just don't work at all. And that actually happens semi-regularly. It's the most common impact of space weather. The other thing that happens when the ionosphere gets thicker, it actually does get thicker. It expands out into space because it's been heated up. And that means if you have low altitude satellites or the International Space Station, things from 400 to 600 kilometers altitude, they experience increased drag and start falling out of the sky. I mean, not the end of the world dropping out of the sky quickly, but they will have to fire their thrusters to rise back up again to the right altitude more often during active periods. Sometimes this is a good thing, right? There's a lot of space junk in low Earth orbit, so whenever there's a big solar flare, we lose a bit of space junk, which is a great thing. So pros and cons. The second thing that happens, or big impact, is the radiation. So SEP stands for solar energetic particle, and it means basically that snow that we saw in that video from the coronagraph. So this radiation comes and it hits satellites. It can charge them up and cause electrical arcs, which will obviously damage electrical equipment on the satellite. It can charge up not just the surface, but also the inside of the satellite and cause discharge inside. That's possibly even worse than surface discharging. And it can also hit the computer chips inside the satellite. So just like radiation damages the DNA in your body, radiation will come in, hit the ones and zeros basically in the binary of computer memory and disrupt them. So if you disrupt enough of the binary inside a computer system that's actually working, it will crash. So we see a lot more what are called single event upsets, which basically means a little glitch in an onboard computer during high amounts of radiation. If you have too many of those in too short a time, the satellite can crash. And then, it depends how you designed your satellite and how badly damaged it was as to whether you can recover it. We talked about aircraft as well. So, during these intense SEP events, if you're flying particularly over the North or South Pole, then you get an increased radiation dose. So there's not many routes that fly over the North or South Pole, but there are some Mostly Europe and America to China and Japan are the primary routes. And a solar flare, unfortunately at the moment we can't predict them. We just see them happening. But when they happen, the intense effects last 20 minutes to a couple of hours. So it's that kind of time scale that we're talking about. Well, that very much depends on solar activity. So during solar maximum, when there's lots of sunspots, you can have large flares every day nearly. So, I mean, there's flares all the time. Right now, if we went and looked at the sun, we'd see some A and B class flares. They're just a continual process. X class flares, the really big ones, are a couple per solar cycle. M class flares is sort of 10 to 20. So we had an M class flare last year and a couple the year before. They cause radio interference and things like that, but and satellite operators have to monitor that for the radiation and satellite purposes. But you probably didn't have any big problems last year due to solar flares. That's a great question, and actually it leads into this slide, which is the kind of time history of satellite disruptions and solar flares. So in the top right, we actually have a time history of the radiation measured in space, going all the way back to the 70s. So you can see it's cyclical, like the solar cycle, and during the maximum intervals, you get these big spikes due to solar flares. And this is a logarithmic scale, right? So a solar flare is 1,000 times more intense than the average background sun. This is a time history of computer failures on certain satellites. So here was not last solar maximum, but the one before. So unfortunately, I'm not sure if this graph is normalized. Number of satellites is always going up, but there was a peak in the number of disruptions to satellites at solar maximum. This plot at the bottom shows intense solar flares during the Apollo moon missions. So these numbered blue lines are the Apollo missions to the moon, and you can see Apollo 13, Apollo 14, and Apollo 16 were just incredibly lucky, right? They launched and went to the moon outside the Earth's protective magnetic field, came back again, and didn't die. Whereas, if this had happened during those missions, the radiation dose, maybe not instantly fatal, but they would have had radiation poisoning at least. So right now we don't have astronauts going to the moon. They're on the International Space Station, which is 400 kilometers altitude, so they're quite protected. But NASA wants to go to Mars. If you're going to Mars, it's a 2-year trip, right? So this is a serious, serious problem if you want to go outside the Earth system. So let's look at a recent example of SEPs, and that was the Halloween storm from 2003. So the video I showed you earlier with all the CMEs and the white snow, this is the same event. So here is a picture of the sun from those couple of weeks, and you can see really big, grubby-looking sunspots, 3 groups of them on the sun. So these are the culprits for all the solar flares that happened in those couple of weeks. So in about 2 weeks, there were 143 flares. So here's a different answer to your earlier question. The average rate might be 1 a day or so, but at solar maximum, you can get 143 in 14 days, right? And 80 CMEs. So again, normally there's 1 or 2 CMEs a week in terms of on average, but in this 2-week period, there were 80. And okay, you can work out the recurrence times for yourself, but this resulted in a very intense radiation environment that was continually being topped up over this 2-week period. So there was a very long interval of very intense radiation that bombarded satellites. What happened, there's a few different effects. Satellites, I hope you should be learning this, have star trackers to orient themselves. Star trackers are susceptible to radiation in the same way the coronagraph is. The star trackers get washed out, they can't tell what stars they're looking at, and they start turning the spacecraft around. If it turns around too much, it might lose track of where it is completely, and then you've got to recover the satellite from the beginning. That radiation also damages satellites in terms of electrostatic discharge. So in this particular, this 2 weeks where we had this intense radiation, it's estimated that 59% of satellites were affected in some way by the radiation. And the real experts are here in the room, but one satellite was permanently lost, and a couple had really serious problems that required several months to fix, to sort out. The other impact the radiation has is on solar panels. So this is, SOHO is a spacecraft that sits out in front of the Earth at L1, the gravitational balance point between the Earth and the Sun, and looks at the Sun. So that coronagraph video I showed you earlier is from SOHO. And this is the voltage, is it voltage or current? Doesn't say. Let's say voltage coming off the solar panels on SOHO. And here's a big radiation event. There's a big radiation event. So the surface of the solar panels is being bombarded by radiation, and it is ruining the semiconductor structure of the solar panels and decreasing their efficiency. And obviously, at some point, if the efficiency of those solar panels or the power output drops too much, the satellite's not going to be able to operate properly. So that's radiation impacts on satellites. The final big impact we mentioned earlier was ground-induced currents. So an example of this in the past is from 1989, when there was a very large geomagnetic storm. So here is a picture taken from space. Hopefully you can tell that's Florida. This is the east coast of the United States, and Canada is underneath this big white patch. The big white patch is not snow. This is aurora. So this is washed out in white because there's very, very bright aurora all over Canada. What that means is strong electrical currents flowing through the atmosphere all above Canada, which induce currents in the Canadian power grid. As I said before, those currents themselves don't cause direct damage. What they did do was trip the safety systems on a step-up transformer in a hydroelectric dam in Quebec. And that is when this happened. So the entire power output from the dam was dumped to ground instead of going into the Canadian grid system, and it just melted the transformers. That caused a blackout in Quebec that lasted 9 hours in the middle of winter. So this, it's estimated, I think, a few tens of billions of dollars lost in terms of productivity and so on. They did get the power back on within 9 hours, but it took them many months to rebuild those transformers and get the facility back up to kind of nominal operating. This doesn't just happen in Canada. This is a map of the US. This is the blackout that Canada experienced, but transformers were damaged all across the northern US, or there were some kind of transformer effects, and the power companies had to manage them. Here's this transformer just outside New York was damaged, and so this is the kind of not even the most extreme event, but a large event, and it's what the Americans are considering in terms of their vulnerability to space weather right now. This can also happen in Europe, so we have had power upsets on the national grid due to space weather, nothing dramatic. There have been blackouts in Sweden. Basically, the further north you are, the closer you are to the North Magnetic Pole, the more at risk you are due to these currents. I don't think we need to fear this exactly, but the power outage is perhaps the most economically costly of the impacts of space weather. And in some sense, that's useful because we have some warning. We can see a CME coming towards us. We can forecast its arrival time. We can give power companies some warning that some unusual currents are going to appear in their system. So in the UK, that is done by the British Geological Survey and the Met Office Space Weather Operations Centre, MOSWOC, which is in Exeter. So BGS is in Edinburgh and MOSWOC is in Exeter. And together they make maps like this. So here's a map of the UK. Each circle represents a high voltage transformer in the UK national grid. The size of the circle represents the amount of current flowing through that transformer due to geomagnetic storm. So you can see that the regions of highest impact are in the Scottish borders because they're more northerly, and they also have very resistive rocks under them. So, the more resistive the ground is, the more the current wants to flow through the electrical infrastructure. So, Scotland is perhaps the place with the most risk in the UK. It's not just blackout that can happen due to space weather and the electrical grid. Excuse me. The price of electricity is also due to, supply and demand. This is electricity price in red. Geomagnetic storm intensity in red, and then the amount of power available in black, and the amount of power drawn in blue. And this is from America. And what you can see is during this geomagnetic storm, supply and demand were almost equal. And that meant that the electricity in those 2 or 3 hours was very expensive. And they only avoided a blackout by asking some industrial factories to reduce output for a couple of hours. And these authors, Forbes and Sincere, have estimated that space weather costs the US economy several hundred billion in terms of electricity cost over a decade. So it's not an insignificant cost. You don't notice it, it's just part of your electricity bill. But your electricity bill would be a little bit cheaper if we didn't have these space weather impacts. So okay, that's all of the impacts that we can have here on the Earth. How do we deal with this in terms of risk? So the UK government works on what's called a reasonable worst case scenario basis. So the UK has an official reasonable worst case scenario for space weather, and that is based on the discovery of space weather by Richard Carrington in 1859. If you're interested in this stuff, you can go to the Royal Astronomical Society or the Greenwich Observatory and see the original measurements made by Carrington here in the UK. So what happened in 1859 was an incredibly large flare and a very fast CME. They didn't know that flares or CMEs existed at the time, but Carrington saw the flare, and 17 hours later, the magnetometer that was measuring the magnetic field of the Earth at Greenwich went absolutely crazy. So this was the discovery of geoeffective CMEs. So here is the trace from that magnetometer. It comes along like this. You can see it jumps up a little bit, and then it dips down off the bottom of the page. Very luckily, someone was paying attention, some smart geophysicist in 1859, and they quickly pulled the piece of paper down. So then it did this, and then it went off the page again, so then they put the paper back up again, and then it came back on here, right? So unfortunately, we don't know the offset of that. We do know that this is pretty much the biggest geomagnetic impulse ever measured at Greenwich. So, luckily Greenwich wasn't the only magnetometer in the world. We have similar magnetograms from Germany, India, many other places around the world. So we can definitely definitively say that this geomagnetic storm was the biggest recorded geomagnetic storm, although we don't always have very well calibrated data. Here is Carrington's drawing of the sunspot. You can see this at the Royal Astronomical Society. So there's a couple of white kidney bean shaped things here. That's the solar flare. These dark regions are the sunspots. So you can see that this was a very complicated, messy sunspot, and it's complicated, messy sunspots that cause the biggest solar flares. So he actually saw the light from the solar flare with his telescope, and from that we know that it only took 17.5 hours from then until the geomagnetic storm on the Earth. And that means that the CME must have been traveling at 2,400 kilometers per second. So what makes a very intense geomagnetic storm? It's when that rate of reconnection from the front of the Earth round to the back is fastest, and it's when the Earth is squeezed the most by the solar wind. So a very fast, very intense magnetic reconnection event creates the largest storm. So going 2,400 kilometers per second means it's definitely very fast, and it must have had a southward pointing magnetic field direction, we would expect. So this is the UK's reasonable worst case scenario. What happened in this event was the telegraph, which had, the internet of its day, between Europe and America, managed to run without batteries. Some telegraph operators got electric shocks. There's reports of fires being started in telegraph offices. So we don't really know exactly what the impact would have been on modern technology, but there definitely were large ground-induced currents. The aurora was visible down to the equator, so we know that pretty much the entire world would have been affected. We can also hazard a guess with such a fast CME, the shock wave would have been very intense, therefore the radiation environment in space would have been very intense.
You also assume that the duration was quite long.
We know the duration, yeah. So it did last sort of 2 or 3 days. So yes, yeah, absolutely. So that's the reasonable worst case scenario, or the largest event that we've measured.